Hello everyone, welcome to lesson 414. Our goal today is to compare solutions to equations and systems graphically. All right, so we're going to take a look at equations and systems kind of like side by side and just talk about the differences between them and what it is we're looking for when we have an equation versus when we have a system of equations. All right, and we're going to focus on the graphical part, but we're also going to explore that extraneous solution one more time today to make sure, like, if we do need to verify an extraneous solution, we know how to do it. All right. So just as a reminder, what does it mean to solve a system? This was from yesterday's lesson. We say when we solve a system, we're trying to find values for x and y, and I bolded and underlined that because when we solve a system, we need to find a value for x and y that makes all equations in the system true at the same time. Right? So if I look down here, this is a system, and you'll notice that you see the x and the y in the system. Okay, so when I find my value of x and y, I want to be able to plug those values in, and this would end up being a true statement. I would end up with the same number on both sides for both of these equations at the same time. All right, but it's real simple to find that x and y value. As long as we use the graph, we can plot the two functions and look for the intersection point. All right, so let's take a look at an example of that. So again, just pointing out the differences here, we see a problem presented to us as an equation, right? So in an equation, we're only going to see one variable. We only see x, okay? And it's presented as, something equal to something else, right? So we have this square root function set equal to this linear function, and we only see one variable. So this is an equation, okay? And then over here we have a system. It looks very similar to the equation, right? Because we see both the left and the right hand side. So this is the left hand side of the equation. It actually went into the first function, and the right hand side of the equation went into the second function. But it's presented in a different way. It's presented as a system. Okay, and the system is just a collection of two or more equations. All right. We see two variables here, so that means when we solve a system, we have to find x and we have to find y. The way that we find that is the same for both, right? So whether it's an equation or a system, the way that we solve this graphically is this. There's no difference. We can use the same exact graph. We take the left-hand side, we graph it. That gets us this curved part right here on the graph. We take the right-hand side and we graph it, and that gives us our line here. Okay, and since the equation wants to know when they are equal to each other, these two functions are going to be equal to each other when they occupy the same point at the same time. That would be the intersection point located right here. This is when they are equal to each other. All right, same thing with a system, right? If we want to solve a system, we just graph the first function, graph the second function, which is literally no different than what we did for the equation. Okay, so the solution strategy is the same for both. And we're looking for the same thing. We're looking for that intersection point to find our solutions. So I'm just going to note the intersection point here. So I notice that it is at 16, 6. All right, and then you just want to remember, like, this is an x-coordinate, right, and this is a y-coordinate. And if I go to my equation, we're trying to find out when these are equal to each other, right? What value of x makes these two things equal? Well, 16 would, right? Because at the intersection point, x is 16. So I'm going to say, there's my solution, x equals 16. I found that by looking at the intersection point. Now for a system, just slightly different, right? I want to know x and y, right? So I want to know when they're equal, and I need to know the value of x and y. So I look at my intersection point. Well, they're equal when x equals 16 and when y equals 6. All right, so we find both x and y for the system. All right, now you're going to notice this thing here. It says extraneous solution. All right, so we talked about this in a previous lesson where sometimes when we solve something algebraically, we get more than one solution from the algebraic technique, but when we go and we look at the graph, we only see one intersection point. That means one of your algebraic solutions is what we call extraneous. In other words, it's a false solution. It's not going to produce a true statement when you plug that value in. All right. So if I'm looking at this graph, I can see there is only one intersection point, so there may or may not be an extraneous solution. One is possible. The only way to find out is to take our equation and solve it algebraically. right? And I'm going to walk you through that so you can see it one more time, because there is a lot of stuff that goes on in this equation. None of it is anything you haven't seen before. So here we go. I'm going to draw my line. And one of the first things that I notice is that I have a square root over here on the left-hand side, and my x value is trapped inside of that square root. So I'm going to get rid of this square root by squaring both sides. Okay. I'm squaring to cancel out the square root. So whatever I do on one side, I have to do on the other. So if I square the left-hand side, I also have to square the right-hand side. Now when I square over here, the square root and the square, they cancel each other out, and we just get 4 plus 2x, right? So now the square root is gone, and then over here we get x minus 10 squared. And you'll notice that I just reversed the order of those two terms, so this is still equivalent to this. All right, so now I actually have to square x minus 10, and to do that I'm going to use a box. Okay, so I got to multiply x minus 10 times x minus 10. This is what it means to square it. Okay, so if I do x times x, I get x squared. X times negative 10 is negative 10x. This would also be negative 10x, and then negative 10 times negative 10 is a positive 100. Okay, so I'm going to rewrite this, right? Remember we talked about all that rewriting earlier on in the semester. We're taking an expression and rewriting it using multiplication. Okay, so we're going to get x squared. And then if I add these two guys together, we're going to get minus 20x, and then I have plus 100. Okay, so we took this, we multiplied it, and this is what we got back. All right, so now I see a quadratic appearing in my equation. So we like our quadratics to be set equal to 0. So what I'm going to do is I'm going to take everything on this left-hand side, and I'm going to move it to the right-hand side. I'm going to start with the 4. So I will subtract 4 from both sides. 4's cancel, so we get 2x equals x squared minus 20x plus 96. And then I'm going to go ahead and move the 2x now. So I'm going to subtract 2x from both sides. Okay, so these will cancel, leaving us with 0, which is what we wanted. And then we have x squared minus 22x plus 96. So we're in a good place right now. This is a quadratic set equal to 0, so we should be pretty familiar with what to do here. You have two options. You can go to your quadratic formula and use that to find your two solutions, or you could use factoring. As you know, I'm a much bigger fan of factoring than the quadratic formula, so I'm going to set up a box in Diamond and factor this thing. This one might be a difficult factor because it does have bigger numbers. All right, so don't be intimidated by that. Give it a try anyways. All right, so x squared is going in the upper left-hand corner. 96 goes in the bottom right-hand corner. And then the negative 22x goes in the bottom of my diamond. All right, and then I'm going to multiply here. I'm multiply this first diagonal to get the top of my diamond. All right, so we got 96x squared. And I'm looking for two numbers that multiply to give me 96 and add to give me a negative 22. So you might have to experiment a little bit. You might have to do a little bit of trial and error because these are bigger numbers. But the two numbers you should come up with here are negative 16x and negative 6x. All right, so if I multiply those, I get 96. If I add them, I get the negative 22. So that fills in my other diagonal. And then I start getting my outside dimensions, right? We need x times x to get x squared. We need x times negative 6 to get negative 6x, and x times negative 16 to get the negative 16x. So now I can rewrite, right? That rewriting skill keeps popping up. All right, so we're rewriting this in its factored form. So this is going to be x minus 6, and this will be x minus 16. So we took this, we factored, and we got this out. Right, so we put that in, factored, got this new equivalent form out. So now solving this thing is real simple. I just have to take each factor and set it equal to 0. So this one would get me x equals 6. This one would get me x equals 16. So when we looked at our graph earlier, all right, so we do have two solutions here. We got two solutions by doing this algebraically, but remember on our graph we only had one intersection point, and that intersection point occurred when x was 16. So the other solution, x equals 6, would be considered extraneous, because when I go to 6 and I look at my graph, we end up here, and those are not the same point. Okay, so 6, if I were to plug this into my function or my equation, my original equation, we would not get the same number on both sides. It would lead to a false statement. The 16, however, if I were to plug that one in, I would get a true statement. So this one is a good solution. This one is what we call an extraneous solution. All right, guys, so that's how you do the extraneous solution. That's one more go around with that. Let's take a look at this one. All right, so this is another one. It's an equation. Here's a system, right? So remember the difference here, we see one variable and it's set up with an equal sign. Okay, over here we see two variables. We see the x and the y, and it's split apart into two different functions. Okay, so system, equation, the solution is going to be the same for both of these. All right, so it's asking you to graph. Notice that the graph is not here for you, so you have to produce the graph yourself, and you have options for this. You can use your graphing calculator, or you can go to Desmos and you can graph this thing on your own there. All right, so I've got Desmos all set up for us, and let's take a look at our graph here. So you'll notice what I did, I put in the left-hand side of the equation here into part 1. I put the right-hand side into part 2, and I'm going to go get the points that I need here. So when you do this on MyOpenMath, you need the leftmost point. That's going to be this one over here, and that one's going to be at -3, 0. So I'm going to go back to my graph here, and if I were on MyOpenMath, I would plot this point right here, -3, 0. And then you're going to want to get one more point, right? So this point right here at -1, 2 could be another good point for you to use. So I'm going to go -1, 2. And then once you click this point and then you click this point, MyOpenMath will set the rest of the curve for you. All right, so you just got to get 2 points to graph that thing successfully. All right. Now the second function here, the -5 plus 13 over 29, I'm going to show you how to do that using a little slope-intercept form, okay? So remember, slope-intercept form is y equals mx plus b. Okay, so the number in front of x represents the slope, the b value represents a y-intercept. So this is our b value, this is our slope right here. Okay, so our b value is at -5, so I'm going to plot that point first. That gives me one automatic point. I don't even need to look at Desmos to do that. I just recognize, like, hey, this is the y-intercept. Okay, then this is a slope, and remember, slope is rise over run. Okay, so this 13 represents a rise, this 29 represents a run. So I start here, and then I count up 13. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then my run is 29, so I'm going to go to the right all the way to 29, which would be right here. And then we would draw a line between those 2 points. Let me see if I can do that. It's kind of tricky. Okay. There we go. So there's my line, and then I'll do the radical part, or the square root function, in a different color here. And this one's going to be freehand, so don't make fun of me here. So we would have this curve, and it goes like that. And that's me trying to graph with this pad. All right, so there you go. All right, so this is what your graph would look like, and it's pretty similar to what you see here on Desmos. All right, but really what we're interested in is this intersection point that occurs about right here, and we can verify that intersection point here on Desmos at 29, 8. Okay, so I'm going to come up here and I'm going to say, hey, we've got an intersection point at 29, 8, and that's really all we need to find our solutions here. So for the equation, we just need the x value, so we would say x equals 29, and then for the system, we need the x and the y value, so we would say 29 and 8. Okay, so there we go. There's another rundown of a problem like that. And let's do one more. This one a little bit different, right? Got a different shape graph going on. no problem, right? I've already got a graph for you. So when we solve these things, right, here's our equation, here's a system, right? It's the same thing, right? Just one has only x's, the other one has x's and y's. This one's been split apart. Okay, so the solution method is the same. We graph left side, graph right side, graph function 1, graph function 2. That's what we did over here. All right, and now all we need are the intersection points, which I see 2 of them located here and here. Okay, so this intersection point is located at -5, -4. And this intersection point here is located at -2, -1. Right, so we got 2 intersection points. And I'm going to write those down up here. So sometimes MyOpenMath will just ask you for the intersection points, right? And you just write them both out, separate them with a comma. Right? If they ask you for solutions, make sure you get the x values if it's an equation, right? So this one's an equation, so all we need are the x values. So we got -2, and then the other solution would be -5. Okay. If they're asking for a system, then you need to find both x and y. Right, so our y values are here and here. Right, so we've got -1 and -4. So we want to write these as corresponding pairs. So this one is going to be -2 and -1. Those two would go together. And then down here we would have -5 and -4, and those two would go together. All right. All right, guys, that's it for today's lesson. I hope you found that helpful. If you have any questions, let me know. Have a great day.